If you're a programmer, you might have heard of Lisp. Lisp has affected the programming field in many ways, pioneering quite a few modern programming patterns we use today, and building a reputation of being one of the most elegant programming languages ever conceived. Lisp has had a long and interesting history, growing from its original intention of being a practical mathematical notation for computer programs, to becoming widely used in the artificial intelligence field, and inspiring hundreds of later languages and dialects. Now, to fully understand the impact Lisp has had on the computing field, we must go back to the 1950s with a language called IPL, or Information Processing Language. IPL was created around 1956 by Alan Newell, Cliff Shaw, and Herbert A. Simon at the RAND Corporation and the Carnegie Institute of Technology. It was initially built to run on the Joniac, a room-sized computer made by the RAND Corporation. IPL is considered to have invented the concept of Lisp processing, a paradigm forming the foundation of Lisp itself, along with a number of other features that are thought to have been first introduced by the language. However, IPL had an assembly language styled syntax, which later helped lead to its demise. Newell, Shaw, and Simon, the guys I just mentioned, also authored the first artificial intelligence program called The Logic Theorist, which actually went on to prove 38 of the first 52 theorems in the famous Principia Mathematica. This program was implemented in IPL and laid the foundation for modern AI research, introducing several concepts central to the field. At this time, the term artificial intelligence hadn't been invented yet. There was a man named John McCarthy who would coin it a year later for a conference on the topic. In this conference, Simon and Newell would proudly present their logic theorist, but received a lukewarm reception. However, logic theorists would go on to leave a lasting impact on the entire field, and is considered to represent a major milestone for artificial intelligence, and even the understanding of our own intelligence. In the same summer of 1956, John McCarthy, the same man who coined artificial intelligence, described his desire for an algebraic Lisp processing language for artificial intelligence on the IBM 704, which at the time had not supported IPL. In fact, it wasn't until IPL version 5 in 1958 that support for the IBM 704 was implemented in the language, and by this time, a competitor was taken over. McCarthy had heard of IPL's Lisp processing, but needed a language for the IBM 704, and around this time, he was to serve as a consultant to a program for proving theorems in plane geometry, run by IBM. IBM was also generously establishing a New England Computation Center at MIT, which Dartmouth would use. This is where he would develop a few different programs, and eventually where the birth of Lisp would take place only a few years later. In the fall of 1958, John McCarthy became the assistant professor of communication sciences at MIT. He aimed to start an artificial intelligence project along with Marvin Minsky. However, they needed funding and permission. At the time, the MIT Research Laboratory of Electronics had a contract from the Armed Services that permitted great freedom to the director in choosing and initiating any projects that seemed to be of scientific interest. The director at the time was Professor Jerome Wiensler. McCarthy proposed his project verbally, and Wiensler accepted, providing them with a room, 2 programmers, and a secretary, as well as a key punch. The only requirement was that they were to supervise some of the 6 mathematics graduate students that the RLE had taken under to support. Over the next few years, the team would focus on building an artificial intelligence program like the Logic Theorist, but naturally, they needed a language to write the software in, specifically a language with Lisp processing features, like the one McCarthy had been envisioning ever since the conference. Originally, the idea was to build a compiler for the Lisp that would generate IBM 704 machine code. However, this was considered a major undertaking, so they opted to hand compile everything while they experimented. During this time, they had used a different style syntax than the common S expressions parentheses that became popular. This syntax tried to resemble Fortran 1 and included square brackets with commas as listing eliminators. This was soon dropped in favor of the popular S expression style, and work was done on a paper documenting their design. It's strange to think of it today, but at this time there was still no program that could execute Lisp. Back then, computer time was valuable, and programs simulated their code on cards before even thinking about executing it on real machines. Unlike today, where we can run thousands of tests in a matter of seconds with the ability to easily jump in and change whatever code is causing issues, programmers had to take an idea from pseudocode to machine-specific code, and then finally to actually submitting the code for execution, which could take hours or even days to receive a result, because there was often a queue of other programs waiting to be run. Recursive Functions of Symbolic Expressions and Their Computation by Machine, Part 1, was published in the Communications of the ACM in April of 1960 by John McCarthy. In this paper, McCarthy outlined a programming system called Lisp, short for List Processor. He designed it for the IBM 704 and even described some of the challenges and workarounds for the specific 36-bit word size of the IBM 704 had. While he did write about the design of the language, he actually didn't implement it for the IBM 704. At that time, it was only pseudocode. After this publication, Steve Russell, computer scientist who developed Space War, compiled the evaluate function pseudocode in the paper into IBM 704 machine code, and to McCarthy's surprise, the first working Lisp interpreter was born. Tim Hart and Mike Levin completed the first Lisp compiler in 1962, written in Lisp itself. This compiler introduced the Lisp model of incremental compilation, in which compiled and interpreted functions can intermix freely, which is how some modern JavaScript engines operate today. This compiler included styling, which is closer to modern Lisp than the original described in McCarthy's paper, and also built on the existing API. Around this time, a number of Lisp forks were starting to circulate, which would later lead to a problem. McCarthy started planning a Lisp version 2, but dropped it due to the computer it was initially designed for supporting less features than desired. Subsequently, a version called MacLisp was developed, adding to the Lisp feature base and driving more popularity to the language, while also squashing a few forks. Fast forward a little to 1975, when it was still difficult to implement the Lisp system due to the primitive compiler techniques and hardware of the 1970s. As a result, Lisp ran slowly, and people were seeking a solution. To meet this demand, several manufacturers began creating Lisp machines. These machines were dedicated to running Lisp environments and programs directly on the hardware. This led to greatly improved performance and efficiency of existing Lisp code, and also saw the growth of more dialects with hardware-tied features, and even multiprocess or multi-threading as we would call it today. As I alluded to earlier, the number of different dialects and branches of Lisp were seen as a problem. There was a whole bunch of different syntaxes and codes that were not compatible. So in the 1980s and 90s, a great effort was made to join all the other dialects together into one unified standard that defined Lisp. This new standardized language was called Common Lisp, and in 1994, ANSI published the first Common Lisp standard. However, this did not help the declining interest in Lisp until the 2000s, when Lisp experienced a resurgence. This resurgence can be contributed to the, quote, eye-opening experience that many new Lisp programmers describe. You may have experienced this when first trying the language. The simplicity and power combine into an elegant language that may not be highly practical, but rather more inspiring, causing us to really think about what a language is in its purest components. I even argue that it's this simplicity that leads to so many dialects and forks. The language is easy to parse due to its limited set of keywords and syntactic sugar, and equally as easy to execute, with code and data being intermingled, and stored in one generic container that's easy to loop over. Today you could say that Lisp is still used, not in its pure form, but rather through closure and scheme, to inherit its style and nature while bringing more modern tools and APIs into the mix.